Okay, well, good afternoon, everyone. Great to see you all here. Welcome to EECS151 251A Introduction to Digital Design and Integrated Circuit. We're halfway through the semester, really almost there. And in today's discussion, we'll follow up our discussion on really thinking about the delay of the circuit, right? How we can actually reason about the delay of different components. Last lecture, we were mostly focusing on inverter, right? A single inverter is basically can be viewed as an RC circuit, and then we can see how different components actually affect the delay of the inverter. Today, we're going to expand a little bit. Instead of single inverter, what if we actually chain a range of different inverters together? Because when we think about circuit, it's never just a single gate, right? There are always a range of gates getting connected in a network. Before we get to actually generalize to any random gate combination, we'll stick to inverters, but we'll focus on how we can understand the inverter delay, especially a chain of inverters, from actually a high level, a more principled way to reason about the delay. Since we are talking about the delay, I find it's a good time to actually discuss some of pretty historical moment, at least for my generation, actually, when we think about the Intel and AMD, the war between Intel and AMD, right? We talk a lot of between how different companies have different cultures and they have their ups and downs, right? If we look at the history of AMD and Intel, there are a lot of, I guess, collaborations, but also fights, trying to see who has better x86 processors. For a while, I remember like what I remembered actually when we first looking at different processors, basically Intel was the king. It's just like Intel has the best processor, period, right? Especially in the 90s, it's just like Intel really dominant. That's like the processors that I grew up with. What really changed our generation in the way of actually thinking about Intel and AMD is actually really the battle who can actually reach the first 1 gigahertz processor. And this happened in around 2000. I assume it's like before you were even born, right? You folks are a completely different generation at this point. It was like historical for, at least for my generation. When we look at it, it's actually very close. It's basically on the trajectory for both Intel and AMD. We know their next generation will be able to actually hit 1 gigahertz. It's really become who can actually get the news, well, who can actually get their chip earlier, who can also get the news out earlier. And that's also during a time when AMD is actually doing pretty well. They have been actually delivering very reliable processors for the past couple of generations, really playing this catch-up game very well. So finally, at this echelon generation of AMD, this is the first like 1 gigahertz processor, happened early 2000. When we actually have the first gigahertz processor. Intel was not that behind. So at this close, it's really more just like marketing strategy and like operational management who can actually get things out a little bit faster. Intel was just like a couple months late with this game. But that's really a very important indicator of when AMD can actually produce very good quality processors that can actually even can really actually fight against Intel. So this is the one with ups and downs of Intel and AMD. This is one of the crossover point when actually AMD delivers a better, at least spec-wise, a better processor in this processor war. I think we are also observing a different ups and downs, and these days is also interesting to see the dynamics between Intel and AMD. It's really hard to say which one is better now. But this is a very interesting moment. I still remember it, just like the surprises people have. It's like, oh, wow, AMD reached this first. So it's an interesting moment, but AMD was actually the one who built the first x86 1 gigahertz processor. Well, to reach the frequency, we need to understand the delay, right? So that's what our lecture is trying to do. Why, like some companies, some vendors can actually build faster circuit, and what kind of delays, what kind of components affect the delay of the circuit. With that, let's get started with today's lecture. Just a recap, we talk about MOS transistors, the individual transistor, we can actually view that as switch. We talk about NMOS and PMOS transistors, and we use NMOS to do our pull down network so that we can get very good ground zero. And we use PMOS to do the pull up network so that we can get very good ones. That's basically the CMOS design, right? They are always complementary to each other. We always have both NMOS and CMOS. We also talk about inverter delay. Last lecture, we talk about even like we see an inverter, just like we flip the value, right? But it doesn't happen immediately. There is what we call propagation delay, right? It takes time to propagate the input signal to output signal. And when we discuss the delay component, right, we basically view this as the RC circuit. And we think about at a high level, the components involved in deciding the delay, those are basically the resistance of our transistor, our gates, and also the load and parasitic capacitance, right? Both the R resistance component and the capacitor component affect the overall delay, right? The bigger our load is, it takes longer to charge and discharge our circuit, so the delay is longer, right? If the resistance is actually high, it also takes longer to charge and discharge your circuit, so the delay is also high. So those are the two components. We talk about the time constant tau here, basically related to the resistance and the capacitance of our RC circuit. With that, we are going to actually talk a little bit more about how we can actually size a transistor, in particularly size the inverters, right? We talk about inverter can be viewed as RC components. You may already hear when people say, oh, for this circuit, we need a bigger drive because this is a little too weak, we need a bigger drive, right? What do people really mean when actually say a bigger drive, especially in the context of integrated circuit, right? So today we're going to talk about, when we actually talk about NMOS, CMOS transistors, they're not actually just a fixed module there. There are some flexibility that we can actually size the transistor, and that will actually affect the delay behavior. So that's actually a very interesting and important knob for circuit designers to actually modulate the delay, really when it comes to sizing the transistor. So let's take a closer look. Just a recap, we talk about our MOS transistor model, right? We have a gate, we have source and the drain, right? We talk about the dimensions associated with the MOS transistors. We talk about the length of our gate. Typically, we actually talk about the minimum feature. This is basically the feature size. The length of the gate for each technology is pretty fixed. But another parameter, very important, is the width of our channel, right? We talk about if we have a wider channel, things we have actually get more electrons, things can actually flow faster, right? So that will change basically the amount of current we can flow. If we also have a wider channel, it will also affect the capacitance, right? Both the gate capacitance from input perspective, and also we briefly talked about last lecture, right? Also parasitic capacitance, that also associated with the dimensions of our transistors. So let's take a closer look, right? So input capacitance, this is basically the gate, like we basically view this from input, right? When we can see the input, then basically the input is connected to both the gate of the PMOS and also the gate of the CMOS, right? This can also be viewed as basically two capacitors. So we say input capacitance, when we see other gates, we'll see a different combination, but in this particular case, we think about inverters, right? From input point of view, my input is connected to both the PMOS, the gate of the PMOS, and also the gate of NMOS. When we actually charge and discharge, we need to actually charge of the input, we need to actually charge the PMOS and NMOS capacitors there. So that's one of the input capacitors. We'll talk about people talking about the input capacitors of the gate, right? Over CMOS gate. These are basically the gate capacitors here. So now when we actually come to the dimensions, we talk about we can actually have a bigger drive, or I have a bigger CMOS. Typically, we don't typically modulate the length. So we mentioned like that's basically the feature, right? The feature size dictated by really the technology roadmap, right? All those different nanometer technologies, that's basically the length of the gate, the length of the channel. What we can do actually from a circuit and fabrication perspective is we can actually make things wider. We can actually have bigger channels, right? So that the current can flow through a wider channels that can actually flow faster, right? when we actually have a bigger channel, if we think about this as a capacitors, right? This region, we basically also have a bigger area, right? The plate has a bigger area. You think about capacitor, a capacitor is basically have bigger area. You can actually charge and discharge. You need to actually charge and discharge more charges onto the capacitor plate, right? So when we actually make our circuit, make our transistors bigger, more specifically wider, that also means we actually make our capacitance bigger for at least first for input capacitance, right? Because I have a bigger cross-section area under the gate. We also see similar things with a parasitic capacitance because the weights actually affect all the dimensions of our MOS transistor. So this is what people call input capacitance, right? So this is a width. Basically, we're introducing this width dimensions of our MOS transistor that actually give us a new parameter that we can change when we think about circuit delay here. So that's weights for input capacitance, right? We briefly talk about the parasitic capacitance. So that we mentioned it's basically the overhead. It's not directly related to functionality, but it's basically the overhead will actually do switch our circuit. It will also need to charge basically this parasitic capacitors as part of the our MOS design. When we think of parasitic, again, this is actually looking from the output, right? So we need to charge the load. We also need to charge the parasitic. Those are, and we mentioned earlier, to get good ones for both PMOS and good zeros for NMOS, we always connect the drain. So this is always a drain node to our output, so we can get good zeros and also good ones, right? So we think about parasitic capacitance. Again, this is also largely set by the dimensions of our CMOS circuit, right? So you have a bigger plate, we have bigger area, we need to charge, we have more charges that we need to charge and discharge, right? Similarly, for inverter, again, we look at from the outside, it's connected with both PMOS and NMOS, the drain of terminal of PMOS and also the drain terminal NMOS, right? And similarly, right, whenever we actually make the size bigger, it also means we actually have a bigger parasitic capacity. So that's basically the overhead we need to consider, right? We'll also talk about this later, but that's also keep in mind when we actually make the make the dimension bigger, we also increase the parasitic capacitance. So typically we use this gamma constant to describe the relationship between our drain capacity, basically the parasitic capacitance, and our gate capacitance, basically the input capacitance. Different textbook, different technologies use different gamma constant. For most recent, especially the more advanced technology, those two become pretty close. For our discussion, we just use one. We don't differentiate. Basic gamma is one. We just the parasitic is actually significant enough. It's actually comparable to the gate capacitance for advanced technologies these days. So it's getting more important. But overall, we want to see really introduce this dimension of width of our transistor that we can modulate. And by modulate that, we'll see that in a minute how it actually changed time. But at the first glance, it definitely changed the capacitance and also resistance of our circuit. So that will actually introduce interesting delay behaviors when we think about our circuit. Questions, comments? Make sense? Now we have a new parameter, right? We can play with. Let's see what we can do with our new parameter. So this is basically, we'll hear people talking about the sizing, right? When they actually want to size the gate, size a transistor, size an inverter, or size the general CMOS gate. They are basically trying to modulate this width parameter that we just introduced, right? It's basically the dimension of our CMOS circuit, and that can change both capacitance and also change the resistance of our circuit. So for example, when we actually see you may hear people talk about, oh, let's put a size 2 inverter here, we need a bigger drive. What they really mean by size 2 inverter is basically the width doubles, right? The width doubles, so both the PMOS width and also the NMOS width doubles compared to our size 1 inverter. So size 1 inverter is the baseline, but you can actually get bigger size 2 or size 4 inverter. And fundamentally, it's basically doubling the width that we discussed earlier. And we mentioned earlier, we'll get a bigger size inverter, right? our input capacitance doubles because we have a bigger plate. Similarly, our parasitic capacitance also doubles. We also have a bigger plate, right? And at the same time, from the resistance point of view, right? When we talk about resistance, it's linear, it's proportional to the length. You have a longer of the material, the resistance is higher, but it's actually inverse proportional compared to the cross-section area, right? So you will have a wider, bigger channel. The resistance is actually smaller because current can actually flow in all the directions, right? So that's a property of resistance. So with that, with a bigger W, with a wider circuit, wider NMOS, our resistance actually is smaller. So with a smaller resistance, if you recall, our current, right, Ohm's law, current is actually voltage divided by resistance. With a smaller resistance, again, with a bigger transistor, size 2 transistor, our resistance actually smaller, right? And then our current actually gets bigger. So that's what people mean actually when we say, oh, we need a bigger drive. Drive here just means we have bigger current, right? We have a bigger current. We can charge faster. We can also discharge faster, right? So this also affects our current flow because now our resistance also smaller by having actually large area, larger MOS, CMOS transistors. So this is a very powerful parameters, very useful when we actually think about delay, and it affects the amount of charges we can accumulate. It also affects the current we can actually deliver. And when we actually get things bigger, typically when people say bigger drive, they basically mean bigger current so that we can actually do charge and discharge faster here. Make sense? Right, so that's a new parameter like we're introducing. Before everything is pretty abstract or simple, right? Just inverter, NAND gate, right? That's it. But here is even for inverter, there is actually a new parameter that's actually very useful.
So if the capacitance doubles, does it charge faster?
If the capacitance doubles, does it charge faster?
Yeah, does it need more charge or 2 times the charge?
Yeah, so we'll see actually in a minute. So here there's also input capacitance and output. We're actually charging the load and discharge the load and parasitic. We'll see in a minute that, but it's actually more related to the ratio between the input capacitance and the load capacitance. So this is the the drive I have. I'm more related, but I'm driving some circuit actually, or some gates actually down the line. So it's more like the relative ratio. We'll see that in a minute, the relationship here. But definitely the parasitic capacitance is also bigger, so that's also a factor when we think about it. So there is a trade-off there. You make the current smaller, but the parasitic is actually parasitic capacitance is what we need to charge and discharge. That also gets bigger. So that's also, there's a trade-off there. We'll see in a minute the relationship. Any other questions? Okay, so now we have this parameters, right? What we can do with this parameter. So one thing people actually used to do a lot is less important, less significant these days. I guess like Vector maybe also asked this actually last lecture, right? So we have PMOS and NMOS, right? So typically, we also talk about the propagation delay of both low to high and high to low, right? Typically, we want to have a symmetric delay. We want to have the same low to high and high to low delay, so that's easier to actually reason and also optimize our circuit. In the past, typically, the mobility or resistivity of PMOS and NMOS actually are pretty significant different because PMOS is actually conducted by holes and NMOS is actually by electrons, right? So different mobility, so PMOS is typically slower. So when we actually see, especially with old technology, we'll see the design. PMOS is actually typically bigger. It's sometimes actually funny. It's very interesting if you look at some of the older designs, especially older generation technology. When you see that, you can see actually a much bigger, like bulkier PMOS because PMOS need to be much wider so that it can actually match the rate of NMOS. So that's what we typically see actually in older generation of technology. In newer generation technology, it's getting actually very close. The mobility of PMOS and NMOS, resistivity between PMOS and NMOS is getting pretty close. So in our discussion, unless actually explicitly specified, we want to capture the different mobility. We typically size PMOS and NMOS the same because Now they have relatively the same ability in modern process technologies. There's no reason to size it differently. So we just size PMOS and NMOS the same. But in older generation technology, when we actually talk about transistor sizing, a very important use case is actually to size PMOS and NMOS differently so that we have a balanced high to low and low to high propagation delay. Make sense? Questions? All right, so now we see some of like the internals of our inverters and the way we actually reason about delay components, right? So far we're mostly talking about the intrinsic behaviors of inverters here. Most talking about the intrinsic behaviors of the inverters. Now let's put it in context how we actually reason about this when we think about delay, right? So last lecture, when we talk about the delay, right? We talk about, we can view this as an RC model. And when we actually drive it, like to Brendan's question earlier, we actually charge this load capacitor. This is the output, right? So this is the capacitors that's being either charged or discharged when we connect to a PMOS or NMOS. In addition to the load capacitance, we also mentioned this parasitic capacitance. So now you'll see where this fits in, right? That's basically the drain capacitance that we talk about in the MOS design. So this is a parasitic capacitor. We also need to charge. So those are the two capacitors that we need to charge. Those are actually the designs actually down the line, right? Those are the design we are driving here. So we talk about the propagation delay here. It's basically the longitude of our time constant, RC constant here, right? So here it has two components here. We have our resistance here, and then we have the two components, both parasitic and the load, right? So similarly, there are also two parts. There's some people call this part, basically the parasitic, the delay of charging and discharging the parasitic capacitor, what they call parasitic delay or intrinsic delay. Basically, as the name suggests, this is intrinsic to this gate. No matter whether we are loading a bigger circuit or smaller circuit, this is independent of the load, right? This is only intrinsic to the circuit design. So when you hear people talking about intrinsic delay or parasitic delay, this is basically largely dependent on the design, on the inverter design, or basically the gate design itself, right? How much parasitic capacitance we have, what's the resistance we have. Question? Mm-hmm.
Is the input or gate capacitance also factored in parasitic?
That's a good question. So the question is whether the input capacitance is also factored into a parasitic delay. It is not. So if you look at our MOS transistor as a switch model, the input capacitor is actually not connected to the output. It's only controlling, so input capacitance is actually basically the load from the previous stage. The previous stage is actually charging and discharging my input capacitance, but my input capacitance is actually disconnected from my either a parasitic and load, right? So everything on this side is what I need to charge and discharge, but input capacitance is really just at the gate level to control this switch, whether it's on and off. So we actually don't, for this current stage, we don't charge our input capacitor, but the current stage is basically the load of the previous stage. We'll see an example later. So the previous stage needs to actually charge this, but it's parasitic here doesn't include the input capacitor. Mm-hmm. Good question. Any other questions? So this is purely parasitic. So that's why it's intrinsic to the parasitic. What we discussed earlier, we say that basically the size or capacitance of parasitic is pretty close to input capacitance. So it's just a way to approximate those two. But when we actually charge and discharge this at the current stage, input capacitance is not involved. So when you hear people say parasitic or intrinsic delay, this is basically what they are talking about. The delay we need to actually charge and discharge our parasitic capacitor. So there's also, well, it's just a little bit like more work every time. We actually need to reason about all those factors, the resistance, parasitic capacitance, the load capacity, just a lot of factors, right? When we talk about this lecture, what we're trying to do is really view this from a more principled way. And we like to actually just simplify it so that we can actually reason about the complexity of our circuit. right? So just with a couple rewrite of basically the same behavior we discussed earlier, we can basically talk about this gamma parameter, right? We can put it in, and we can take the input capacitance out of the parentheses, and then we get what we call basically it's gamma together with a ratio between load capacitance and input capacitance, right? So we are not doing anything fancy here. All we're doing just doing a bunch of circuit like equation rewrite, and in particular just take this outside the outside the parentheses. So we have this ratio here. So what you will see a lot of time when we actually talk about delay, especially in the high level to reason about delay, it's actually we typically use a much simpler either equation or using a much simpler, really the strategy. All of the reason we try to simplify it is that we can actually reason about this directly. So what we are doing here is by rewriting this, we could actually get a much simpler expression to express the delay here. So here, instead of having all those vectors, we have this tau of inverter or this delay of the inverters, and basically very similar to what we have earlier, the intrinsic or parasitic delay of the inverter. So this is a constant that we use for our inverters, and this is actually independent of the transistor size. You look at this as both the resistance and the capacitance here, right? Resistance is the inverse and proportional to the width, while capacitance is actually linear proportional to the width, right? So this cancel out the width. So this constant is actually independent of the transistor size. So we take this constant out, the entire delay become very simple. It become one part. It's basically the intrinsic delay we discussed earlier, right? The delay we need to actually charge and discharge the parasitic capacitance. And another part we'll hear actually fan out. That's also a term that you hear a lot. So fan out is really just how many things that we're driving. So the delay, of course, is related to the intrinsic property, the parasitic capacitor that we have. But the very important part is this fan out. It depends on how big of a circuit, how complex a circuit we are driving. And that complexity also dictates this delay. So that's what this part fan out trying to do, this kind of ratio between load capacitance, load is basically what we're driving, and also the input capacitance, basically the intrinsic capacitance of our circuit. So with that, a lot of time when you actually see people reason about delay, it's actually very simple. They just have the two terms here. They have a constant. This is basically parasitic delay. Intrinsic is always there. There's also what they call effort delay. So the reason it's called effort, because this is really just like how much effort we need to make so that we can actually drive a circuit, drive the gates actually after me. So at a high level, again, you may realize like circuit designers, when we talk about of course, there's a very complex way you can actually talk about equations, talk about circuit analysis. But again, the principle, when we think about the principle of design, we typically try to abstract it to a higher level. And eventually, when we think about delay, of course, we can do it with different terms before, but eventually this becomes to intrinsic parasitic delay of my gate myself, and also the amount of load that we are driving, right? If we're driving more load, we have bigger load capacitance, right? I need to pay more effort. I need to pay more effort, and it also takes longer to fully charge and discharge my load capacitance to actually settle to either a clear 0 or clear 1, right? So then my circuit will be slower. If my load is smaller, it's actually faster to charge and discharge. I have a smaller effort delay, my circuit will be faster, right? So eventually it's boiling down to the two components: how much parasitic I need to charge, and how much load, like the later stages have, that I also need to charge. And this charge is both components will affect the overall delay of our circuit. Makes sense? Those two components, right? At high level, we need to control ourselves. How fast we can move also depends on how many things that we're dragging, right? So that's basically the high level principles of thinking about delay with those two terms, parasitic delay and effort delay. Okay, with that, let's look at a simple example here. So we talk about inverter delay, right? We can also talk about, we also talk about the width, the new parameter that we introduced, right? We can make the NMOS and PMOS size bigger here. So what if, how the inverter delay would actually change if we actually, if the width, the W parameter we talk about, both PMOS and NMOS of the inverters are basically doubled. If we make both PMOS and NMOS wider, right? Will that be faster, right? It's the size 2 inverter. Actually, this is actually slower, right? The propagation delay is actually longer. Would that be slower? Would that be faster? Right? Or would be the same? Now we actually change, make things wider, right? How would the overall delay of my gate actually change? Take a look. I put some equations here. You may or may not actually need those equations, so that's why I grayed out. But more we are thinking, no, okay, there's the parameters. I make it wider now, right? Would that make my circuit slower or faster, or more or less the same? What do you think? Vector? It would be faster. Why?
Because in this case, if we consider the rates are like double, then the input capacitance of both the PMOS and CMOS will also be double. So, and given that the load capacitance is not changing,
Right.
So CL over CE would be half of the original time. So the total like delay would be half of the original.
Right, that's a good point. Yeah, so as Vector mentioned, right, we have we make our both PMOS and NMOS bigger, right? So now our gate capacitance is also bigger, our input capacitance. So we make ourselves stronger, basically, by make things bigger, right? We make ourselves stronger. And as Vector also mentioned, the load doesn't change, right? What we are actually driving doesn't change, but we ourselves become a lot stronger, right? We can charge and discharge a lot quickly. Now we mentioned the delay is really just a ratio between how big we are, how strong we are, and also how strong or how big our load is, right? The load doesn't change, we become a lot stronger, so we can actually make things a lot faster, right? Cedric.
Where is the current increase in those equations?
Right, so Cedric is wondering where does the, so we say faster is the current needs to be bigger, right? So where does the current, why is it actually so faster, but we actually don't see the current? We don't see the resistance. Well, I guess we abstract away the resistance here, right? So when we actually make things wider, another way to look at this is when we make things actually wider, our resistance is actually smaller, right? So we have lower resistance. With lower resistance, we also have higher current here, right? So our current become much higher. We can also charge and discharge much quickly. So that's also, it's also factored in. It's actually also part of the argument. You can look at from both ends, but that's why it's actually become faster. So that's the resistance.
So why do people want small transistors and not super wide transistors?
Yeah, so now it's like, oh, it's always the bigger, the better, right? So we'll see actually in a couple of slides later. So it's not actually, when we think about circuit design, it's not only sizing an individual transistor or individual like inverter or general gate. It's typically in a network, right? When I have a network of the gates, it's not only just how strong individual transistor is, it's also how strong relative to others, and you want to have a more balanced design. With a balanced design, it's not typically not the case. The bigger, the better. You actually want to actually like consider both what things in front of you, what things after you to actually get a balanced design. So in most of the cases, not the bigger, the better. We'll see actually in a couple of slides. So very good question. So typically it's faster, but it's also related to, so far we'll still only look at the single inverter, right? We'll put it in context with our circuit network, and in a lot of cases, it's not actually just the bigger, the better. Very good observation. Any other questions? Vector.
So I'm wondering, like, would there be a trade-off between the like delay and the like throughput? Because, for example, if we're given a certain like size
Yeah, that's also a good question. So that's also a very important trade-off, right? So I guess it's a little bit indirect because the more transistor we have, it doesn't really guarantee that we get a bigger throughput, right? So that's a little bit, there's some indirection there. But yes, there is also a trade-off. We'll actually also see sometime in circuit design, it actually makes sense to actually make transistors either bigger or smaller. So, but sometimes it actually makes sense to actually make more transistors or make more gates put together that could actually potentially optimize the delay. But then we step out even more, but at high level, delay and throughput are two different optimization metrics, right? So we talk about the 1 gigahertz race, right? Back then it's how we actually get to as high frequency as possible, as lower delay as possible. But throughput, a lot of today's parallel processors, they are really optimizing for throughput, right? So they actually don't actually get super like high frequency of each individual core. They actually want to get more cores. So that's an important trade-off. It's also, I think there's a lot of factors involved in, but this also plays, I guess, a small factor of that trade-off. But that's a very, very important, but also very good observation there. There's a bigger trade-off there. We'll see in a more limited context, but by either adding more transistor, adding more gates, or making gates bigger, those would have different delay behaviors. Yeah, we'll see in a minute. Any other questions, comments, observations? Okay, so now you know when people actually, oh, Will.
Sorry, yeah, I had a question here.
Sure.
Why exactly is it faster if also our delay has, like, we're multiplying by CN as well? Like I understand the fan out is reduced, but we also have that part. So
right.
Yeah,
so that's a good question, right? So we mostly focus on the fan out part, right? But as Will mentioned, there's also this component, right? So we mentioned we abstract this component into tau, and this is actually a size independent parameter. The reason it is actually size independent, if you think about the relationship between resistance and the capacitance, right? With a wider width, our resistance actually gets smaller, right? We have a have a wider channel, right? We can actually flow faster, right? You have a bigger W. Our capacitance actually go up, right? Because our plate is bigger, right? So when we're actually changing the width here, while the resistance and the capacitance, each of them are actually changing, as a multiplied result, the RC constant here is actually fixed. It's independent of the size. So that's why when we say this tau parameter is actually independent of the transistor size.
Thank you. Yeah, that answers it well. Thanks.
Right. So the resistance does change. It just cancel out because the capacitance also change. Okay, good question. So now we see when people say make a bigger transistor, right? What they are trying to do here, right? They basically want to modulate the delay change. Announcement. Not a lot of announcement actually this week. Just lab 6 starts. This is our final lab, right? Get started early and wrap up lab 6 also early. We'll actually start our project. We'll release a project before spring break so I can take a look and see. And the checkpoint, especially getting checkpoint 1 started. I'll mention more next week, but checkpoint 1 is very simple. You don't need to do any coding. Just draw your pipeline diagram, right? The only thing is really want to make sure you get started in thinking about your project, right? So project release next week, not this week. This week still focusing on the lab, but do take a look at the project overview once you started and start thinking about your pipeline, how you would like to actually draw it. And we will have a new homework this week. The homework will cover basically the materials from both last week and this week, basically the CMOS transistor and gates module. Shouldn't be too bad. We consider this will be a busy week with all the labs and the project coming up. So it's a pretty light homework. You should be able to start basically after this lecture. So you should start early and then so that you still have time to focus on the lab and the project. Okay, any questions? Things are going well? Takes more time with the lab. Okay, yeah, do go to the lab. It's a good opportunity to interact with others. And the project is really the fun part. I was talking to some of our alums yesterday, and they still remember the time they spent in Corey basement doing 151 project. That's one of their highlights of their Berkeley experience. Definitely, well, if you feel it's not that fun, remind yourself when you, in retrospect, when you look back this journey, this will be really, I think they actually told me, maybe just I was there, they try to like not really impress me, but just mention this class. But they mentioned this is actually one of almost the only class that has this significant project component that they feel like they were able to do a pretty interesting end-to-end design during their undergrad career. So this is definitely the highlight of this class. I'm always very excited when we get to the project component. I hope that also translates to our students. So get ready, the fun part will start very soon. The project. Okay, with that, so we already hinted earlier, right? So far we still, now we talk about inverters, right? We can actually size the inverter. We just look at the individual inverter, right? It doesn't feel like a space of optimization, right? Just like the bigger, the better. Of course, there's area cost, right? But the bigger, the faster, right? Let's just make big transistor. This may not be the case when we actually put our inverter in a chain, in our entire circuit network. Again, we'll start with a chain of inverters. Let's focus on the inverters first, how we can actually minimize the entire path, and then we'll actually talk about how we can also generalize this to arbitrary gates. So inverter chain, right? As the name suggests, it's basically a chain of inverters. So here is like we zoom out further, instead of looking at each individual gate, we look at a circuit here, right? So this is well, basically one of the simplest circuits we can have, right? Just inverters. We just put a bunch of them together, form a chain, right? And then it drive a load towards the end. This is actually commonly used when you hear people talking about buffer, right? They need a buffer. It's typically means basically a chain of inverters, right? If you have equal number of inverters, it won't actually change your values, but it actually can potentially actually make your signal stronger after a chain of buffers or chain of inverters. So that's what we mean by inverter chain. Some terminology you will see that when you actually do circuit analysis, right? So here we already mentioned earlier, so we have a chain of inverters, right? Each of the inverter of the next stage is really the load of the previous stage, right? So here the load, let's say, of the, I guess let's do this is I, and this is I plus 1, right? The load of the I stage, this I stage is basically driving the next stage, right? What it's actually driving is basically the input capacitance. So far, before we were mostly talking about parasitic capacitance and the load capacitance, right? And we say the input capacitance is actually disconnected from the left-hand side of the drive, right? So now you see where input capacitance is actually used, because input capacitance for the next gate, for stage 2, is basically the load capacitance of stage 1 here, right? Because stage 1 is actually driving, stage 2 is basically driving the gate of stage 2, right? So the load of here specifically of stage 2, the load of stage 1 is basically the input capacitance of the next stage, the stage 2 here. All right, so now you'll see the relationship. Now we actually start using our input capacitance now. So input capacitance is basically the load of the previous stage, right? And when we say N is basically a number of inverters, right? So here we have N inverters. So typically we basically assume when we actually look this way, the input capacitance, we just do a normalized, the input capacitance of the first stage is 1, so that we can actually reason about it. It's just everything is actually normalized to the input capacitance of the first stage. So everything so far is basically the problem setup, right? So all we're trying to do, this is the setup of the problem, represent a commonly used actually circuit. And when we actually want to make our circuit faster, fixing the critical path delay of our circuit, it basically comes to we can also remove different modules, right? That's also a different discussion. But here, in particular, we think about transistor sizing. With this setup, it's basically given this chain and given this load capacitance, right? We do have this flexibility, assuming the circuit is actually fixed now. We do need to actually implement this a number of inverters, right? So this is the setup, right? We do have the flexibility of size each transistor differently, right? We talk about this new parameters we introduce that we can actually change the delay, right? So how do we actually size those each of the inverter in the chain to actually minimize the delay, right? So this is a very specific example, but this also show up a lot. Like everything is fixed now. So now, but this is the new, not necessarily new, but there's the additional parameter of the transistor sizing we can play with, right? How do we actually size each of the transistor, each of the inverter here in particular, so that we can actually minimize the overall delay of our circuit? So those are my setup. This is a problem actually we see a lot when we think about optimization, think about the delay, because this is a very powerful tricks that we can do to actually not changing the circuit topology, but do get our circuit faster. So how do we actually consider this, right? We do have what do we have earlier, right? The delay is just two factors: the parasitic delay associated with myself, and also the fan-out delay, the effort delay associated with what I'm actually driving, right? So let's basically write down the delay before we optimize it, right? Let's just write down the delay. What are the different components associated with the delay when it comes to a chain of inverters, right? So you may hear people, again, like sometimes we also want to demystify some of the terminologies. Those are pretty straightforward, but people use like weird terminologies. When you hear people say path delay, right? It's basically the entire path of the circuit that we're discussing. So that there's nothing fancy about it. It's basically the path delay. It's basically what we are trying to solve. This is basically the path, and the delay is basically the path delay, right? So that's when people say, oh, let's minimize the path delay. It basically makes things faster of the entire path. It's basically a delay of the propagation delay of the individual gate, right? So you would just write down the propagation delay of each individual inverters, and then let's use our delay terminology, delay equations we had before, right? This simplified delay equation. Now you see it's actually a lot simpler to use this instead of using a bunch of like ln to RC parentheses, blah, blah, and blah, right? So it's just a lot easier. So you see why people are actually doing that. We just change it so that everything become 1 plus the fan out, right? The fan out is basically the load I'm driving. And for the first stage, what we discussed earlier, the load is basically the input capacitance of the second stage, right? So the fan out for the first stage is basically the input capacitance, which is a load divided by the input capacitance of my current stage. So similarly, for each of the stage, the fan out is basically the input capacitance of the next stage and my own input capacitance, right? Again, what I'm driving, the ratio between what I'm driving and the stress of myself, right? So that's basically the fan out, right? And then another term you may hear, again, related, right? Path fan out. This is basically, instead of fan out the individual stage, for the entire path, right? What I'm actually driving, right? So in this case, again, this is a path, right? The path fan out is basically the eventual load that we're driving in the end after a bunch of inversion, after our circuit. That's this load we are driving, the ratio between this load we're driving and the input capacitance from the input perspective, right? Ignore everything in between. This is our load and this is the input, right? So the path fan out is basically the load capacitance divided by the input capacitance, right? So that's basically the setup. Now the problem really becomes, we already know the path fan out, right? We know the load capacitance. We also know the input capacitance, right? Those are outside the circuit. So we're given a path fan out. So this is given. We already have this pass fan out F, right? We want to get the mean of pass delay. This is the delay of our circuit, right? So, and the pass delay, which is basically, well, we have a bunch of n here. N plus n is because we have a lot of one here, right? Like get the ones out is basically F1 plus F2 plus all the way to Fn. The pass fan out is given, and the pass fan out, the capital F, is basically the multiply of everything, right? Everything multiplied together. That's what we have here, right? Because they cancel each other out, everything in between, right? So pass fan out is also basically the fan out of individual stages being multiplied together. So that's another way to look at the fan out. So basically the fan out of the entire pass is the same as the multiplied result of fan out of each individual stage. Okay? So this becomes a very standard optimization problem. Given a fixed product of all the terms, what we want to do is minimize the sum of all the terms, right? So that's a problem. We know the product of all those terms, they are basically our fan out. And we also know the delay that we're optimizing is basically there's constant here, some constant plus the sum of all the fan out. There are different ways. Don't worry about the equations. I basically wrote the equation again here. Different ways of question. Mm-hmm. Oh, right. So the reason I add n, so we basically start from here, right? We just put all the ones to the front. There are a bunch of 1, and then a bunch of F1 plus F2. Right? We just separate the one part, the constant part, and those ones, I wrote that turn into an n. So you basically, all the parasitic delay actually added together as a constant. Right. Yeah, so that's where n is coming from. And then we just group all the f's together, right? So we talk about this is basically an optimization problem. We have a fixed fan out and we want to minimize the delay, right? There are different ways you can solve it. You can just get the derivative and make the derivative 0. You can also, I think there are also some, you can use a geometry to solve it. But basically, once you have a fixed product of a bunch of numbers and you want to minimize the sum of a bunch of numbers, the sum is actually only minimized when all the numbers are the same, which kind of makes sense in this way. Especially, I really like this analogy when we actually think about delay. Basically, delay is minimized when each stage have the same delay. So you have, let's say, a fixed delay. We have a fixed number of stages. We want to minimize delay. Instead of either doing a lot of things at the very beginning and then procrastinate towards the end, or just procrastinate at the very beginning and then try to do everything at the last minute. Both of them are not optimal. The optimal way to actually solve or finish a task is to distribute that task over a time frame and move towards your goal every milestone along the way, so that the delay is basically distributed, your effort is also distributed. That can actually make things a lot faster. So that's drawing analogy here, but there are different ways you can solve it. Basically, you have fixed the stages, and all those efforts multiplied result is a constant. It basically is minimized when each stage has the same. So you want to have actually a balanced pipeline. You don't have a big front end of the pipeline or a big like tail of the pipeline. You want to distribute your efforts basically evenly. So you're making your progress along the way. That will actually minimize the overall delay. That applies to a lot of things. I really like it because we introduced this when we started the project. A very good reminder, we have 3 checkpoints. We balance that effort out. So the best way to minimize overall effort you spend in your project is to actually make constant progress across towards your checkpoint. That will actually minimize overall delay. So back to our circuit. So again, this principle also applies to our circuit. So delay is minimized when actually every stage has the same delay. here. So with that, basically every stage has the same fan out, have the same F, right? The lowercase f here. So we can actually calculate the F here. And then if everything has the same F, the overall, the same fan out, the overall path delay is basically the constant N we discussed earlier, and then N times the fan out of each stage. So that will be basically the minimum path delay that we can achieve. Make sense? Questions? This is a setup. Basically, we try to, when we think about circuit, we like to actually get things balanced, right? So that they will see this as an inverter, as an example. We'll see an example later. This a little bit abstract. We'll see an example in a minute. And this also applies when we actually see more complex circuit. So let's take a look at an example, right? So this is the setup we had earlier, right? So we have 3 stages. So we have 3 stages now, and it's 3, right? Our load capacitance is 8. Our input capacitance is basically 1 here, right? So the overall path fan out is basically CL divided by the input of the first gate, right? Which is basically 8, right? And in 3, right, we talk about to achieve the minimum delay, we want to evenly distribute the effort, right? Which means each of the fan out of the individual stage is basically square root of the overall path fan out, right? So N is 3, right? And then we have a 2 to the power of 3 is 8, right? So each path fan out is 2. Right, so overall fan out is 8. We want to distribute evenly for each of the stage. The fan out is 2, right? Then eventually we still want to size the transistors, right? How would that actually affect the size of the transistor? Let's say for the first stage, 1, right? We talk about basically the fan out of stage 1 here. The fan out here is basically what we are driving. The driving is basically the input capacitance of the second stage, right? And what we are, which is the input capacitance of my first stage. Because this is 2 and my input capacitance is 1, which means the input capacitance of side of my second stage is basically 2, right? So now we actually know the size of the second stage, right? We want to double the second stage so that we can actually get a balanced pipeline. And similarly, we can also look at those 2, right? So now we know the input. So now again, the input capacitance of the third stage, second is also 2, right? Which means the input capacitance of the third stage is basically 4, right? So we size this inverter with the size 4. So again, this is basically achieve this balanced pipeline, right? So for each of the stage, the fan out is 2, right? And then overall, the fan out they will evenly distribute the effort. So that applies a lot when you think about circuit design. So now here is the case. I think Brendan, you asked earlier, right? Why don't we just make all the transistors as large as possible, right? So there is also a balance. If you're too big, right? The one before you need to drive a huge load, right? So there is also a balance between different stages. Right. So that's basically how we actually think about the delay of the chain, right? So that you see why we actually want to have a simplified expression so that we can reason about the trade-off, and then we actually group them together. We can actually minimize the delay, and minimize delay. What we are modulating is basically the size of the transistor, right? We can size the transistor in a balanced fashion, then we get a good delay across the entire path. Okay, yeah, good. Well, any questions, comments about our delay? So now you see what, Brendan?
Yeah, so if C in this case were higher than CL, what property?
Oh, you mean if this C in is actually significantly higher than than the load capacitance? So if our input capacitance is much higher than the load capacitance here, so we are actually driving, so the input capacitance, let me think of it. So we have a very strong input capacitance, but we have of the past, we have a very weak load towards the end. And then the fan out basically become less than 1 here, right? So yeah, so the fan out basically become less than 1 here. So which means that, let's say for this stage, it actually need to be sized smaller than the input, than the previous stage, right? So here we just normalize to 1, but the input, like whatever, let's say we put another inverter before, this also of a particular size, right? Whatever size it is. Again, to balance this, this stage need to be basically smaller. So far we basically always size bigger, but it also can also size smaller here. So it's basically the load, the input load is too big, right? And the output is actually pretty weak. We don't need to actually have very big transistors at this point. We can actually do things smaller there. Yeah, good question. So everything we basically normalize here, and everything is relative in this discussion, right? Good question. Okay, so this is basically the way we think about delay here. Right, so this actually have some very practical use, actually, especially when we actually think about overall design, and even when it actually come to circuit design, right? One thing we also see a lot is when we actually thinking about how many stages or how many inverter or how many circuit stages we should actually include in our design or our path, right? Let's say a bunch of inverters, right? Like having more actually don't change our design, or having few, it doesn't change the functionality, right? It's either 0, like from a 0 or 1 perspective, it's either 0 or 1, right? But having different number of stages and also the size of each stage could also potentially actually change the overall delay here. So this is just as an example. Let's say we have 4 different ways of actually designing a buffer, right? We can just use a single stage inverter, or we can actually go all the way 4 stages with the inverter. Here we also size it. If you notice here, we also size it equally, right? We have a very balanced design following our principle, right? We want to have a balanced design here, right? So, and eventually the data path we're driving is also fixed here, a fixed load of 64, right? So here, this actually an interesting trade-off. Let me also relate it to what Vector asked earlier, like the size of the transistor, how many we have, and the size of the number of stages we have, and the size of individual transistor here, right? We don't want to do actually a lot of math here, but here, what we want to do here is just looking at the delay equation here, right? Of course, it is related to the n here. With a bigger n, we may actually have a longer delay, right? Because we have more stages. But at the same time, you look at this term here, right? So with a bigger n, basically more stages, the fan out or the effort of individual stage is also smaller, or the delay of individual stage is also smaller, right? We basically having more stages will make the delay of individual stage actually smaller, right? So there is also a trade-off is actually by having more stages, each delay of individual stage is smaller, but you do actually need to multiply again with a number of stages. Or if you have fewer number of stages, this A is smaller, but the fan out for each stage is also bigger. So there is also an interesting trade-off here when we think about the number of stages versus the fan out of individual stage. If you have time, you can actually go through this because we have actually listed the size. You can actually calculate the delay of each of the paths just to see the trade-off here, right? I'm not going to go through that. Here is if you look at what we have by actually going through the overall delay here, right? So if n is too small, even n is small, it's very dominated by the fan out, right? So we still have a big delay. if N is big, right? Well, each fan out is small, but we do need to actually consider this big factor of N, right? There's some sweet spot actually in the middle. It's more actually balancing both N and the fan out of each individual stage. So that's a high level trade-off here. We're not going to, related to this, you may notice here in this fastest design, we actually have the F, the fan out factor is 4. This fan out factor is 4. You may also notice it's less popular these days. Well, it's still very important, but when you actually see the delay when people actually discuss delay in circuit design, a lot of the time they're basically saying as delay as multiple fan out of 4. So out of 4. This become a constant because typically when we actually think about the stages, typically if each stage actually driving basically 4 with the effort fan out of 4 is typically actually more balanced. So that's also a fan out of 4 is also a very commonly used metric in the design. And you can actually solve this this equation. It will lend to, I forgot exactly, 3 point something, it's basically getting very close to 4 to actually get this balance there. So that's another term you hear it here to use to describe delay, because fan out of 4 is typically a balanced stage for each individual. Okay, so that's the way we actually use this to describe delay. Another way we can actually also help this to reason about delay is when we actually think about circuit optimization. If, like, for example, we have this chain of delays and we size our transistors, inverters correctly when it was a load 64, right? Let's say all of a sudden you are responsible for your module, right? But the module actually downstream and the module that you're driving all of a sudden make a big change. They are making their module more complex. So they actually increase their input capacitance from 64 to 56, and their input capacitance become your load capacitance, right? Basically the circuit you're driving become a lot bigger, significantly bigger. Now it's come to you to actually make a decision, right? So now the circuit downstream actually changed. I still want to minimize the delay here, right? So now to minimize the delay, should we actually remove an inverter, right? So now we have like smaller number of stages, right? We only, instead of having 3 inverters, let's just do 2, and it will be hopefully be faster because we don't have that many stages, right? Let's get a simpler design to actually drive that. Or we actually make things bigger, right? To actually get things more balanced, because all of a sudden the load become significantly bigger, right? Or, well, there's nothing we can do. It is what it is. Let's just well, move on. Well, they change their design. I don't want to touch my design. And that's the spirit of collaboration, but it is also a valid choice. What's your intuition after the discussion? What should we do? At least your gut feeling, like now someone will change their design to make things a lot harder. What should you do or consider to do at least? What's that? And another inverter. This is yeah, this is, well, again, this class intuition is more important. So yeah. So we want to actually add another inverter in this design. We can also, I don't want to do too much math in this class, but again, now my pipeline is not balanced anymore, right? So I have a much bigger load, and I like to have my pipeline balanced and to potentially to reduce it. You can also walk through the equation to see whether it's actually bigger or smaller, but as a general hunch, it's so imbalanced now, let's actually add another stage to actually balance things out. Okay, so that's basically our inverter delay discussion. Just a quick recap, right? So we start from this, like by the end of last lecture, right? This is what we have, right? We want to reason about inverter delay as a RC circuit. But as a very good circuit designer, you still feel like every time writing so many terms are too tedious. I like to actually just write a very simple term to actually normalize to this tau constant and to characterize my delay as either parasitic delay, this fixed constant here, or effort delay that depends on the fan out, right? The load that I'm driving. This is actually still stay the same when we actually come to a chain of inverter, a chain of circuit, right? When we actually draw the path delay here, it becomes basically the sum of the delay of individual stages. We write it this way, you can still group it into two sides, the parasitic delay and the effort delay. And when we actually think about the path fan out effort, right? It's basically the load we're driving and the input we have. And typically what we like to do is basically we size the inverters so that we can actually minimize the overall delay. And the overall delay is minimized when each of the stage has the same effort delay, the same F, right? So with that, we know the individual F, the individual fan out, we can actually calculate the size, the capacitance of each inverter, right? So that's basically how we think about delays. We start from a single MOS transistor, single gate, then we get to a chain of inverters. And now we see it's not always best of our interest to make things as big as possible. We actually need to consider what's before us, what's after us to optimize the delay. So far our discussion is mostly focused on the inverter. And next week, we'll start our discussion to actually generalize this into any arbitrary gates to see how we can reason about delay of any circuit. We'll talk about how we can introduce a new concept, what people call logical effort, to describe that. We'll see more next week. So great to see you all here. Hope you enjoy this part of the lecture, this part of the class, and take care, everyone. I'll see you next week.